Hello and welcome back to the 11th video in the rotational motion series. This is the last video in this series on rotational motion, and I'm going to make this video just go through a exam problem. So the exam problem I've picked is 2016, the mechanics paper, and question 2 all about rotational motion. So it has a ramp, a hollow and a solid cylinder, the same shape and the mass, and they're rolled down the slope. So the first question says, state the energy changes that take place as the cylinder rolls down the slope. You may assume that there's negligible heat and sound energy produced. So energy changes in rotational motion, I've made a video, it's video 8. And there I talked about energy bar charts. So I'm going to look at the energy bar chart for this situation here. So I have position A, which I'm calling the top of the slope. Any of the cylinders have gravitational energy, and as they move down the slope, that gravitational energy, so position B I guess is near the bottom of the slope, has been converted to kinetic energy because they're moving, and rotational energy because they are spinning as well, or rotating. And so that as an equation would be gravitational equals kinetic plus rotational. So instead of as a sentence, you could easily put that in as your answer to this problem. Part B says the hollow cylinder has a radius of that. It rolls down the slope, reaches a speed 0.25. Rotational inertia is given. Calculate the rotational kinetic energy. So there's the key there, the kinetic energy of the hollow cylinder at the bottom of the slope. And again, this is video 8 because this is about rotational energy. So here is my thinking on this problem. The first thing I would think of is, well, in the last question I talked about the energy changes. So perhaps this wants me to do some sort of calculation using the total energy involved. If I'd set that up, the issue is I don't have any information about the height. So that should say can't calculate gravitational energy. So I can't really use the total energy idea to do any calculating here. Okay, so what else do I know about rotational energy? Well, I have just a straight formula for rotational energy, half I omega squared. Let's see if I've got enough information for that. So I have got I, they've given it to me, 0.14, and I can calculate omega if I use this formula here, which relates linear speed to omega, because I've been given the radius. So I have to rearrange that to find omega. Put my numbers in, 0.25 divided by 0.058 gives me the radians per second, 4.31 radians per second. And then I can put this omega into my kinetic, rotational kinetic energy formula. So then I've got that, half I omega squared, put the numbers in, 0.14 times 4.31 squared equals 1.3 joules to 3 significant figures. And 3 significant figures because I've got 3 significant figures here, 3 here, although I've only got 2 here. So it would probably be okay to write it as 2 significant figures, which is just 1.3. Okay, the next question, part C. The hollow cylinder starts from rest and has an angular acceleration of 1.72. Calculate the time taken to complete the first full rotation, one rotation. So it looks to me that it's given me that they've started it from rest. I've been given an initial rotational speed. I want to calculate a time. They've given me acceleration. I have a funny feeling this is going to be the equations of motion, or the rotational equations of motion. I've done a video on that, which is video 5 in this series. So if you want to go back to that if you're lost. What I'd do is I would write down what I've got. Whenever I'm using the rotational, or the equations of motion, I write down what I have. So I have the initial speed from rest is 0 radians per second. I have the angular acceleration, 1.72 radians. That should be per second squared. So sorry about that. And I have this one here, the time taken to do the first full rotation. So this is in words, but as a mathematical thing, one rotation is 360 degrees, or 2 pi radians. So I look for a formula that has all of those, and in video 5 I show them, and you've got them all in your formula sheet, and this formula here has all of the information. There's a shortcut here, because I have omega is 0. 0 times time is 0. So I can rewrite the formula as just this. I'm not going to go through how to rearrange it. By this stage, hopefully you're skilled enough to be able to rearrange it. But to define t, this is it rearranged. Put my numbers in, and I get out 2.70 seconds. All right. The solid and the hollow cylinders are both released at the same time from the top of the slope. Explain why the solid cylinder reaches the bottom of the slope first. Here's my thinking. Again, so I'm not going straight to the right answer first. I'll think about how I think about it as a physicist. So we're looking at a difference between the hollow and the solid cylinders. My first thinking is it's something to do with them being different shapes. One's hollow and one's solid. So then I think, what have I learned in physics about rotational objects that are different shapes? That's rotational inertia. And I think that's video 6, if you want to go back to that to remind yourself about what rotational inertia is. But it basically, the symbol is I, and it depends on where the mass is. So the solid cylinder has the mass spread out from the middle right to the outside, whereas the hollow cylinder, all the mass is on the outside. The hollow cylinder has a greater rotational inertia. So how does this relate to getting to the bottom first? So what I would do is maybe then I'd look at, I know it's got something to do with I. I'd look at my formulas from my formula sheet that have something to do with I in them. So I've got L equals I omega. That first formula is about angular momentum. I probably wouldn't use that because angular momentum, just like normal momentums, you're usually looking at a situation where you're looking at a before and after. Whereas these are rolling down and getting gradually faster and faster and faster. Normally, with angular momentum problems or normal momentum problems, there's some sort of collision or some sort of change happens really quickly. Like the skater brings their arms in really quickly, or a bullet is fired in and hits a rotating object. This is a gradual process, and so that's why I probably stay away from angular momentum. The next one, torque equals I times alpha. So that's about a rotational force causing acceleration. That kind of makes sense because we want to know which one gets to the bottom the fastest. I guess it's the one that's going to accelerate the fastest is going to get there the fastest. So I could use that. The other one's rotational energy, has an I in it. A couple of slides ago we talked about the different types of rotational energy. So I guess I could talk about that as well. I'm going to end up picking the middle one. You could formulate an answer using the rotational energy as well, but we're just going to go with the middle one for this one. Okay, so in my sort of structured answer, I'm going to have the same idea about rotational energy first. Rotational energy depends on where the mass is. And they're talking about the solid cylinder getting there first. So the solid cylinder has a smaller rotational inertia because its mass is closer to the center than the hollow object. So I've talked about the rotational inertia, and now I have to link it to going faster. So I've got this formula I'm going to choose, and now I'm going to explain all parts of it. Not just one part, all parts of that formula to get the right answer. So the object that gets to the bottom the fastest is going to have the greater acceleration, so I'm going to have that by itself in the formula. So rearrange it. Torque divided by rotational inertia equals alpha. So both cylinders have the same torque. So remember, torque is the rotating force that accelerates them. What rotates them, what accelerates them? Gravity. Gravity acts the same on both cylinders because they have the same mass and the same radius. So it's the same in both cases. However, their rotational inertia, their I, is different. The solid one has a smaller I, and because it's divided by that, it's going to have a larger acceleration, and therefore reach, it's not spelled right, reach the bottom first. So there's my structured answer, but also you saw my thinking behind that answer as I got to there as well. So that's a whole rotational motion question. Hopefully you enjoyed the series and you got something out of it. There'll be more series coming up.